Let's get started.
Yeah.
Okay, so today is Lauren Woolsey's PhD defense. Yes. Celebrations to follow at some point, maybe after lunch, but we'll see. Yeah, that's still up in the air. So yes, it's my job to. First of all, it's great to see you all again, and it's my job to do the introduction. I can go chronologically, I guess. I think Lauren's first time she graced our halls here was in 2010, RU undergrad program. She worked with Leonard Strawn on a project that summer between junior and senior year at UMD. And I wasn't part of that project, but I saw her talk, and I was impressed by the fact that at the end of the talk, somebody asked a sort of out of left field question. Maybe it was Bob, and Lauren said, "Oh well, here, let me just go to my extra slides, and I have some more information about that." So extra slides on an undergrad talk was impressive. Harvard also thought that because she came here in fall of 2011, started working with me pretty much immediately on research and on the solar wind that you'll hear about. In 2012, I taught stellar astrophysics for the first time. Lauren was in that class. And there were several times throughout the semester that I think some of the other students who were in that class are here too, where I sort of failed utterly in terms of explaining something. And somebody asked a question about what I meant by some strange thing I said. And I tried again, and Lauren actually patiently waited for me to flounder around, and I think there were a few times where she just said like one or two words, and the rest of the class just said, "Oh." So very good student, very good researcher, and of course now newly minted, soon to be assistant professor, and I guess I should end it there and give you over to Lauren for her public talk.
Okay. So hopefully this is the right volume. Okay, so yes, I am Lauren, and I will be talking today about the work that I've done for the past 5 years on understanding the solar wind and really trying to figure out the magnetic field's role in all of this. But before I begin, just with the dissertation, this is starting with some of that front matter, including acknowledgments. So I wanted to mention a couple of people who have brought the sunshine to my life. So I'll start with many of the friends that I have outside of the department, several of whom couldn't make it but are going to be watching this recording. So hopefully your picture is here if you're watching. And then, of course, this department is just a fantastic place. Both the graduate students that we have lots of shenanigans with, and all of the professors that I have been able to learn from and work with. And it's just really been fantastic. And I wanted to give a special shout out to SSP Coffee. There were several mornings when that was the only reason I got in before 11 a.m. So, of course, my thesis committee is a fantastic group of people who have slogged through that document and given me some useful feedback, and I'm sure we'll have a lot more to say after this. Steve has been a phenomenal advisor, and I am his first student, but I'm very excited to have academic siblings at University of Colorado, and I look forward to collaborating with you in the future. And then we have Alyssa Goodman, who has been my mentor in the student-faculty mentoring program, and Lars Hernquist and John Raymond, who have both been excellent members of my committee and my TAC and have been very helpful with advice throughout this process. And then I'm very happy to have Justin Casper here as my external committee member, who is in Michigan, and I will be neighbors with you in the future. And then, of course, to my family, without whom I would not have been here. Both my family members who were able to attend here, my parents and my sister, as well as all of my other family members that many of whom will also be watching. So again, hopefully you're in this picture. And then, of course, to my husband, Sean, it may sound cliche, but it is true that without you, I would not have finished the PhD. So your support has meant the world to me over these past many years, much more than 5. Okay, and then before I really get into the content of the talk, I want to remind everyone that the sun is a star. So all of the physics that I'll be talking about are the same with stellar physics, but we are in a different regime. So the first star outside of the solar system to be resolved was Betelgeuse, and that was actually work done by Andrea Dupree, who is here in the audience. And since then, there are about a dozen more stars for which we can actually see their disks. And some of them have really weird shapes because they're rotating very quickly, but there's really only a dozen or so stars that we can see aspects of their surface. And then, of course, you have the sun. So this is just a completely different regime for what we are able to do with stellar physics. So this is a picture taken from the Venus transit. That is Venus there. So this sort of gives you a sense of if we were right up close with all of these exoplanet transits, what we could actually do with things. But even more so than that, just noting the types of fine detail that we can see with these observations. Not only can you see exactly where the sunspots are and how many, but also that there's this darker umbra and the less dark penumbra around them. There's so much structure here that we can see because the sun is so close to us. And we don't just have optical wavelengths, we have these really nice extreme ultraviolet wavelengths, where now we're seeing a whole different view of what the sun looks like. So I'd like to point out that where you see these sunspot groups are where we're seeing very bright active regions. These are regions where we have nice loops of plasma that are tracing the magnetic fields. And if I go back and forth, you can see that they're tracing from one sunspot to another. And of course, we also don't just have spatial resolution, we have time resolution. So this is a video of 1 month worth of solar data where 1 day is happening every second. And you can see that there's just so much that is changing here on a day-to-day basis and over the course of the month, that our models have to account for all of this fine detail that we have. We don't just have this one mostly circular shape that we can study. We have all of this detail. So these active regions here, and these darker regions that are called coronal holes. And I'll be bringing those up a lot in the rest of the talk. Okay, so enough boasting about solar physics. Let me move on. So I'm going to start with some of the relevant background material. And for each of the different chapters of my thesis, we're going to see this same picture again. And I'll basically add more and more to our understanding of this picture as we go. So one thing I'll say right now is what we're looking at is a picture that was taken from the ground. Normally, you cannot see the corona from the ground, except when you have a solar eclipse. So this is actually the moon, and you can see some of the craters of the moon here that is blocking the disk of the sun, allowing us to see all of this diffuse material above the limb of the sun. This is how astronomers and solar physicists were able to understand anything about the corona before we started to put spacecraft into space. So we're going to find out a lot more about this type of material throughout the talk. So let's start with the very basics. The sun is powered in its core by fusing hydrogen into helium. That process releases energy, which then escapes the sun. So the entire source of energy in the sun is coming from the center, and it's brought out through a radiative zone and then a convective zone. And this convective motion is something that will come up several times. That's kind of like a pot of boiling water bringing bubbles to the surface. But in this picture, if we have the energy source in the center and we're moving away from it, it's like putting our hand near a fire and taking it further away. We should feel the temperature dropping. But of course, science is not that simple. It is true that the core of the sun is at tens of millions of degrees, and it drops down as you get to the surface. So 1 here is 1 solar radii, that's the surface. But rather than dropping off as you would expect, because you're getting away from that energy source, it actually leaps up to 1,000,000 degrees Kelvin. And this was a discovery that was made in the 1940s, first by Alfvén and then by other researchers who added to our understanding and to the evidence that we have for this. So the part of the sun's atmosphere where this jumps up to 1,000,000 degrees is called the transition region. So we're going from 6,000 degrees, which is the surface of the sun, up to 1,000,000 degrees Kelvin. Then you add to the fact that you have comets. So comets are something that we've been able to find in the records for thousands of years. They're something that are very visible in the night sky. And in 1951, Biermann looked at the dynamics of these comets and looked at their tails. So for those who aren't aware, comets, when they come in through the solar system, their tails are always pointing away from the sun. They're not trailing off behind them as if you had streamers and were running down a street. They're actually always pointing away from the sun as if that's a fan blowing things back. And if you do the science to figure out basically how hard that fan is blowing, you'll find out that it's an outflow that's moving at about 500 kilometers per second. That's a little over 1,000,000 miles an hour. So taking these two understandings together, that the corona is very hot, millions of degrees, and that we have this outflow that is at 500 kilometers per second, Eugene Parker in 1958 came up with this landmark theory that is still very, very useful today, which uses fluid dynamics, hydrodynamics, to say if you have a isothermal, spherically symmetric corona, you have a corona that's at one temperature and it's a very hot temperature, then fluid dynamics predicts that because the sun is at this very high pressure and space is at a very low pressure, that you have to have this outflow. And the hotter that you make your corona, the faster this outflow will get. So about a 1,000,000 degree corona can make about a 1,000,000 mile an hour wind. A 3,000,000 degree corona, on the other hand, can make about a 2,000,000 per hour wind. So this is sort of the basis for our understanding back in the 1950s. And soon after, we were able to make more of the measurements that were able to prove that this solar wind is always there and always present. But it has a whole range of different speeds. So at solar minimum, so let's focus on the left part of this plot for a moment. The length of these arrows is how fast the wind is moving. So at the poles here, at the top and bottom of the plot, things are going at about 700, 800 kilometers per second. Whereas at the equator here in the center of the plot, things are going at about 300 to 400 kilometers per second. We're going to refer to this as the fast wind at the 700, 800 kilometers per second, and the slow wind, the 300 and 400. And what we've found over the course of our observations is that these really are two distinct populations. Not only do they have different wind speeds, but they have very different densities and their chemical makeup. So we have to understand why we have these different populations and what's causing this beyond just the fact that the corona is hot, because you can't get these speeds with the corona temperature that we see. Back in this example, 3,000,000 degrees could get you those speeds, but the corona is not that hot. So there needs to be additional acceleration sort of just beyond this simple idea of a hot corona. But of course, we still also do not understand why the corona is at 1,000,000 degrees. We've just sort of proven, yes, that's true, but we need to know why. And if you go from solar minimum to solar maximum, things get absolutely ridiculous. So now you have fast wind and slow wind coming from all over the place. The colors are all mixed up. I hadn't mentioned those, but the red and blue are basically oppositely directed magnetic field. So you can treat this as it's going out and then coming back in again. So nice loops. That's called a dipole magnetic field. The sun at the very lowest level has this dipole magnetic field. But once you get to solar maximum, there's so many other smaller additions to that you really don't see that overall structure anymore. So we need to understand, if we're looking at the sun at a particular part of its solar cycle, how can we know ahead of time what the solar wind is going to look like? And to better illustrate for you what solar minimum and solar maximum really look like, this is a week's worth of data. This is from 2008. And you can sort of see these nice bright lines here. Those are the streamers, and there's also a pseudo-streamer here. This is actually from the same time that the chapter heading picture is from. And this little interloper is not an alien. It is Mercury. But you can see that there's not a whole lot going on. The bright stuff sort of stays bright, and you can, if you're looking closely, you can see that things are flowing out all the time. But it's a pretty straightforward picture. On the other hand, at solar maximum, this is what I mean by ridiculous. The sun is throwing out these big bursts of material called coronal mass ejections, and that's happening all of the time. So you no longer have this nice equator where the streamer belts are coming from. There's bright stuff all over the place, and then you've thrown out all of this material on top of that. So we need to understand what the solar wind is doing at all parts of the solar cycle, and not just when it's easy. And one of the sort of external motivations for this type of work is that the sun directly affects life here on Earth. So this picture is incredibly not to scale. The Earth would be about 1/10 the size, and they would be about maybe 100 yards apart. But for the sake of artistic representation, this is showing that the sun is here. This is hopefully it will be a coronal mass ejection. But anything that the sun throws at us, whether it's coronal mass ejections, particles from flares, or the fast solar wind, that's all part of space weather. And that space weather hits our protective blanket, the magnetosphere, which is the Earth's magnetic field. And this is what I was talking about with that dipole. And most of it is protected from us, but some of it gets closer in. You can sort of see this yellowish coming down at the poles. That's when we see aurora. So aurora are sort of the nice aspects of space weather, but geomagnetic storms can mess with our power systems, can mess with satellites. There's lots of different things that we really need to be able to understand the sun and be able to make predictions. So this is going to be the wordiest slide in my whole talk, and it will come up again. This is serving as both the outline and the punchline. So this is what I hope to be able to convey to you over the course of the rest of the talk. And this is also the breakdown of the 3 body paragraphs of my work, and they build upon one another. So the parameter study is basically this one-dimensional model of understanding the solar wind coming out of a particular bundle of magnetic field. We then move on to time-dependent turbulent heating, which is also in 3 dimensions. And so we're adding on to the modeling that we can do, but it's still the same process. So now we've sort of added more complexity to it. And then with this 3rd project of magnetic thresholds for network jets, we're looking at a particular example of real-world observations and seeing how well they compare to our models. So we're looking at a particular example of a sphere in this metaphor and comparing it to how well we can actually model a sphere. So in this first body chapter, I'm talking about magnetic fields and a parameter study of all of the different ways that that magnetic fields can manifest themselves. Now, when we look at this picture again, in that introduction, I hadn't mentioned too much what magnetic fields look like. The structure that you see here, so the linear structure and these loops, these smaller loops, and then the more complicated structures, all of that is the plasma tracing the magnetic field. So this is giving us a sense of what the magnetic field probably looks like, but the only way that we can measure magnetic field is at the surface of the sun, and then we extrapolate from that. And these extrapolations look something like this. So this is now work done to model the magnetic field from that particular solar eclipse. And this is kind of what the magnetic field looks like. So there are big loops here. There's some more complicated structures where you have loops together, and those are called pseudostreamers. But you can see, so this is the magnetic field. This is what they model the observations to look like. And then this is that actual picture taken from the ground that we've been seeing several times already. And you can see that the plasma traces the magnetic field lines for us to give us a sense of what the magnetic field looks like. Now, the reason that we care about magnetic fields is they're the basis for the heating mechanisms that are postulated to heat the corona and accelerate the solar wind. There are 2 main processes that are currently possibilities. One is magnetic reconnection, which I'm not going to talk about in my talk, but that one is likely responsible for the coronal mass ejections and the flares that I mentioned earlier. What I will talk about is the Alfvén waves. So Alfvén waves are transverse waves along the magnetic field. And what I mean by that is, let's say that I have a string running from the ground here up to the ceiling, and I shake the bottom of the string. You'll be able to see that wave propagate upward along the string. That is a transverse wave, the fact that you can see the string swaying back and forth, much like you sort of see in this artist representation. And that wave will propagate upwards and then eventually hit the ceiling and reflect back down. If you have two foot points, so this is the solar surface, and you have magnetic field coming out of that surface. If you have 2 foot points, you can basically shake both sides of the loop, and then you have these Alfvén waves that propagate up to the top of the loop, and now they're going in different directions at the top of the loop. And the very complicated sounding Alfvén-wave-driven turbulence can be boiled down to the fact that if you have an outgoing wave and an incoming wave, you will get heating. This is it. The true physics is certainly a lot more complicated, and there's a lot of details that are still unknown. But we can boil down this whole process to, if you have 2 oppositely directed waves, you will get heating. So it will heat the gas and the plasma around it. So if we look at this can certainly happen in loops where you have 2 sources of Alfvén waves. And the shaking that I mentioned is coming from that convective motion. So when we're bringing the energy from the interior of the sun to the exterior, that outward part of the sun has convective motion. And so we are able to shake those flux tubes just as if I were shaking a string that was from the floor to the ceiling. This happens in open magnetic fields too. So rather than having 2 strong sources of these waves, instead, this is the hand here represents the sun's surface shaking the magnetic field. And so if you send the wave along the magnetic field, incident wave, if the environment is changing, so in this case these are 2 different types of springs, but in the sun, as you go higher into the atmosphere, the density is changing and the magnetic field is changing. So the environment is changing. So it's as if you have 2 different types of springs. When that happens, some of the wave will be reflected back down and some of it will be transmitted. As this one goes back down, you send additional waves ahead because we just keep shaking the field. So you'll get outgoing waves and incoming waves lower down, which means heating. And as this one goes up, it'll hit another basically place where the environment is changing and partially reflect as well. And you'll get heating at this whole range of heights. This is the most complicated part of the physics that I'm studying, but it is the most fundamental, that we have these Alfvén waves and they are causing turbulence and turbulent heating. Now, so I mentioned that the Alfvén waves, the whole process cares about how the environment is changing. So as these springs are have different aspects. So the Alfvén waves care about how the magnetic field is changing as a function of height. And space weather currently sort of ignores that. So there's a common use of the expansion factor, which is looking at the magnetic field at the photosphere, so at 1 solar radius, and the magnetic field at this outer boundary called the source surface, which is at 2.5 solar radii. It is a somewhat arbitrary unit, but it's the traditionally used radius. So this expansion factor is simply a ratio of what the magnetic field looks like up here to what it looks like down there. And if you look at the black dashed line and the red open flux tube that I have drawn, a flux tube is just a bundle of magnetic field. They have very different environments in between those 2 values. So the Alfvén waves, as they propagate along that flux tube, are going to have a very different reflection history, you might say. So different heating in those 2 different flux tubes. But these would be given the exact same expansion factor. And even once you put that expansion factor into much more complicated, fully 3-dimensional fluid dynamics, magnetic field models, which are used by the Space Weather Prediction Center at NOAA, you've already thrown away the information that you had low down to create your boundary condition. So one of the big motivations that we had for this first project was to understand how much information are they throwing away and if we could do better. So the first thing that we did was to create a whole lot of example flux tubes. So each line that goes from the left to the right is an example of this red flux tube that I've drawn. As the magnetic field strength drops, that's the y-axis here, the faster that the magnetic field strength drops, the bigger the flux tube is getting, because you have to have the same amount of strength in whatever area you have. So you can sort of treat this as the faster it drops, the bigger it's expanding. And so we created 672 different models that span different field strengths. So these are all user-generated. I created all of those, but we looked at observations throughout the solar cycle to get a sense of what field strengths that we should actually look at, what ranges we should probe. Each one of these now is run through our Zephyr code, which I'll explain a little bit more in a second, but it produces one of these points. So this is now the speed at 1 AU, the speed that we would measure at Earth, versus the expansion factor, that expansion factor that I mentioned, which is just one ratio of magnetic field strengths. The points are color-coded just by expansion factor so that you can better relate back to which types of these lines are creating which of these points. But the key takeaway is, first of all, we do see that as you go to higher expansion factor, you have lower wind speeds. That's something that's seen in observations all of the time. So our models are accurately producing the kinds of relations that we see in observations. But the second thing is that there's not really one line that you can draw through this that does a very good job. There's spread that is 400 kilometers per second at any given expansion factor. So there's not a very good single analytical expression, such as one that you would use for an expansion factor, that can really go through all these points. So we looked at a lot of other aspects of our models to see if there was something that had a better correlation or something else that we could use instead of this expansion factor. And a lot of that's in the paper, and I won't go through it. But one of the things that we did find was strong correlations between the temperatures. So this is the maximum temperature that each model found, and the temperature at 1 AU, what we would measure here at Earth. And this is as a function of the magnetic field strength at the source surface. So it's kind of like the expansion factor, but it's only one part of that ratio. And what you see is that there's strong correlation, more so than the previous plot, especially when you look at just the yellow points. Now the yellow points here are a binned set of models that have 700 to 900 kilometers per second, which is the typical fast wind. Which means that when you look at the most physically accurate fast wind in our models, you actually have an even tighter correlation than the entire parameter study, which sort of has unphysical models on the boundaries of the ranges. So these strong correlations allowed us to build a secondary code. So Zephyr is what we had been using at first, and so it takes the wave properties at the foot points, so how much shaking that you're doing to the bottom of that string, and it takes the magnetic field strength as a function of height, and it solves for a steady state solution to the solar wind you would get out of that flux tube. So you get the temperature as a function of height, the speeds, the densities, everything that you could want, and you get one model every 30 seconds. Because of those strong temperature correlations, we were able to build Tempest. So I wrote Tempest from scratch in Python, and now it's doing roughly the same thing. It's taking the magnetic field strength and the waves, how much you're shaking, and it's now, instead of solving all of the fluid conservation equations, it just solves the momentum conservation equation. We're not conserving energy because we've sort of already done the heating by creating the temperature profiles from these correlations. So it runs very quickly. It runs 45 times faster when it's fully going, and this isn't, I haven't done any optimization or efficiency with the coding. It was just sort of the first steps with Tempest. Now, I mentioned in that previous thing that there's without waves and with waves. And what I mean there is we've actually also been able to take apart the two ways that Alfvén waves matter for solar wind acceleration. The green points here is when you just put in the temperature profiles, but you don't actually put in the waves themselves. So these temperature profiles basically have already done the heating because they're coming from those, the previous model that did all of the physics together. So this is if you just had the hot corona, but you didn't have additional waves. This is what the speeds from tempest would look like compared to Zephyr. And if they agreed exactly, they'd fall along this black line. And then when you add in the waves themselves, they're actually providing an additional source of wave pressure. So not only are the waves creating heating, as I mentioned before, but they're also just creating an additional source of pressure to help push the wind to faster speeds, which starts to help answer the question of Parker's original theory. We can't get the speeds just from the temperatures that we see, and it's because we have this additional acceleration source, the wave pressure. So if both models had exactly the same physics, then the points would line up exactly. And so you can see that the spread here is because we've made simplifying assumptions. But the key part is the spread here is less than when you're just using that simple analytical expression. And it's still a very fast code. So to sort of summarize this part of it, the current use of expansion factor really limits what you can do with space weather prediction. Our parameter study, along with a lot of other things, showed us strong correlations of temperature and magnetic field, which allowed us to build Tempest, which can be used in forecasting. And moving forward with Tempest is something that I plan to do as next steps. So we've talked about that previous work, but now we know that physics is happening in 3 dimensions and in a time-dependent way. So we want to make sure that we're correctly modeling these processes. And in this picture here that we've talked about, you know that this is just a snapshot. We've already seen movies where things are changing over the course of minutes and hours and days. And we want to be able to say more about this than just a single snapshot. So when I have talked about flux tubes, I haven't really shown you one. This is an example of what a flux tube looks like. So it's a bundle of these magnetic field lines. So if we had a lot of strings going from the floor to the ceiling, and they expand, which is what I was talking about when you lose magnetic field strength. So what happens with this code is we shake all of these lines together, and then you start to get much more complicated environments up here that the Alfvén waves are seeing. Now, this plot, the main takeaway here for those who are not familiar with this particular type of modeling is that this is sort of the kind of shaking that we're doing. It's very randomized. It's very random noise generated to make sure that it's just what granulation might do. There's not a single big sweeping motion that we're doing. So the first thing that we wanted to do was to make sure that these models are accurately, are basically giving us similar information to our previous one-dimensional codes. So there's lots of different things we look at in the paper, and again, there's not enough time here. One that I will point out is looking at the heating rate. So when I talked about the heating rate before, this outgoing wave plus incoming wave equals heating, that's sort of what this phenomenological heating rate is here, Qphen, in the dot dashed line. We're comparing it to the numerical result from Braid, which now is 3 dimensions and time dependent and has a lot more physical accuracy. And so you can see that lower down, and so this is the transition region, lower down that heating rate, which was that simple expression that we talked about, is a little too high. So the numerical result is lower, and then it gets to be a little too low. But everything's within an order of magnitude. So it's still a very good expression when you don't have the ability to do all of this more complicated modeling, which is very computationally intensive. We also compared it to a couple of other ways that we can describe how the turbulence is happening. So the blue dotted line is actually what Zephyr is using, the code that we were using in the previous thing, which has an efficiency factor on top of it. And the red is another efficiency factor that might be at play here. So this is basically trying to understand if we can write down an expression for what that more complicated code is doing. And everything's within an order of magnitude. But what we really care about for this code is the time-dependent parts of it. So what is it able to show us that the time-steady code could not? And so this is now showing, as a function of simulation time and height, how much energy is in our code. So you can sort of see this break here at 0.01 solar radii. That's where the transition region is. That's basically where the biggest change in the environment is. So there's going to be a lot more reflection at that point. So you have a lot of strong energy here, but some of it is able to make it past that transition region and provide energy to the corona. And if we look at this in a little more detail, we can basically build up a diagram by looking at a single volume of the flux tube over a short amount of time. And it's basically an event, a heating event that looks at how much heating happened in that volume over that amount of time. And so if we build that up, we get this blue curve here, which has a central point at 10 to the 22 ergs. I'll get back to what that really means. We also compare it to the closed loops. So again, we have with braid, with closed loops, you have two strong sources of Alfvén waves, so you can get lots of heating at the top of the loop. So we did expect that overall heating to be at higher energies. A higher number means higher energies than our work did. But you can also see that our work has a tail here that gets into much higher energies than the closed loop does. And that's because with our open flux tube, we can get to certain times when the environment is just right for a lot more heating, because there's all of this braiding going on. The Alfvén waves are seeing something slightly different. And so there's times when it's just right for extra amounts of heating. Now, 10 to the 24 ergs here is the typical number associated with nanoflares. Nanoflares are a big buzzword in the field because one of the big early ideas for what is heating the corona is these very small scale events called nanoflares that are happening, millions of them every second. And that's what's heating the corona and providing all of that energy to keep it at 1,000,000 degrees. And we're showing that our kind of physics, the physics that we're modeling, can make those kinds of events in a single flux tube. So if it's making a couple of these in this particular flux tube, it can make it in all of them. So the key points of this part here are that the physical processes in open flux tubes occur in 3 dimensions in time. So that's the reason for this particular work. And the results that we found from this more complex modeling agreed very well with our previous work, and it revealed new information to us that we wouldn't have been able to learn before. And one of the big results is that the heating is very bursty and nanoflare-like, which means that the kinds of events that we are looking for should be observable. This is now the 4th time we've seen this, and I haven't mentioned the pink structures here on the edge, in case anyone had noticed them. These pink spiky structures are the chromosphere. So the very diffuse material here is the corona, and the chromosphere is lower down in the solar atmosphere. And it was given that name, chromos, because of the color that you could see in eclipse images like this one. The network jets that we'll be talking about are happening at these sort of scales. They're happening in the chromosphere, so very low down in the corona. So I just wanted to point out where we're looking at in this type of work. So this project would not have been able to happen without IRIS. So IRIS is the Interface Region Imaging Spectrograph that was launched in 2014. And it provided the best view that we have of this chromosphere and transition region to date. So this is the field of view of IRIS compared to a bigger image from Solar Dynamics Observatory. And one of the first things that was discovered in the launch in 2014 are these network jets. So when I use the term jet, I mean something that is collimated, so a nice column of material that is bright and doesn't survive for a very long period of time. So it's a transient collimated brightening. And one of them is highlighted for you here in the red dashed line. And these were seen on the solar disk. So they have speeds of hundreds of kilometers per second at that location, and lifetimes of only tens of seconds. So we wouldn't have been able to see them without something that is taking pictures every 10, 12 seconds or so at the resolutions that we have with iris. This is a time distance plot, and so the slope of something bright here can tell you the speed. And so we wanted to investigate these further because they're very similar to the kind of bursty heating events that we expect from our modeling. And in fact, this is basically bringing those together with our modeling. So this is the time scales of events and their speeds observed. So these are the iris network jets I just talked about. Type 1 and type 2 refer to spicules, which are small spikes on the limb, so in the chromosphere. And before iris, we weren't able to see things that lived on short time scales. So there were only the well-known spicules, which are called type 1. With iris, we were able to see these type 2 spicules on the limb of the sun, as well as these iris network jets on the disk. And this, when you sort of plot them together, it's suggestive that they are in fact the same thing, and we're just seeing them in different ways. This is not unprecedented. For those who know some other terms in solar physics, prominences are something that are bright that are seen off the limb of the sun, and filaments are something that are dark that are seen on the disk. And if you see things in 3D, which we can with stereo, they are in fact the same structures, just how you were able to see them. So this work is very suggestive that type 2 spicules and iris network jets are the same thing. And then these points here are actually coming from our braid modeling. So this is work that Steve and I did that took the Alfvén waves from our modeling and said, if these Alfvén waves can cause compressive waves, so rather than shaking the string back and forth, pushing on a slinky like you might have done in science class, that's a compressive wave. Also, the sound that you're hearing now is a compressive wave. If they can make these types of waves, there can be shocks that lift the transition region. And if you're looking at something bright and it moves upward, it will look like an outflow. It will look like one of these network jets or type 2 spicules. In fact, all of these points come from just that one simulation and looking over the course of time how that might turn into this kind of event. And the black points versus the gray points are simply a cut in how long that outflow would look. So the black points are 2 arc seconds or more, and the gray points are shorter than that, which means they're probably not observable. So the kind of heating that we're seeing in braid can basically fall with the exact same vertical speeds and timescales as these phenomena, and it's suggesting that these phenomena are also at higher or lower speeds and shorter timescales, but they just wouldn't be observable with what we have now. So to investigate this further, we actually turned to the observations to try to understand the magnetic field underneath these observations. So this is just a context image. This is Solar Dynamics Observatory, and this is the field of view of IRIS. So there's 2 overlapping fields of view because I looked at it for several hours. So this big dark spot is a coronal hole, which is a region of open magnetic field and fast wind. So we know that there's a lot of fast wind coming from this area. So it's the kind of region that we had been modeling previously. And so we're looking right on that edge. And so this is what the IRIS data looks like. So there are bright things, and you can already start to see that there's some collimated lines there that look like they could be network jets. This is the magnetic field underneath that same region, and you can already tell that because you can see pixels here and not an iris, iris has better resolution, so we're able to see smaller scale things. But the main goal for this was just to get the overall sense of how strong the magnetic field was underneath these regions. So this is a video of what the iris data looks like for the hour that we were looking. So if you concentrate down here, you can see these long, bright things tend to move around and show up and go away. You can also see all of these black grains, which are actually bright. So this is an inverted image, so it's easier to see these things. All of those bright grains made it nearly impossible for us to come up with an automated way to detect these network jets. So instead, we had to basically do this by eye, at least for this proof of concept study. So what we did was we took this grid, and this is 4 arc seconds by 4 arc seconds, and basically looked at each grid box over the course of the observation and gave it a category. So 0 meant that there was absolutely no jet activity nearby, which, for example, this corner box here or something up here where you can tell there's not anything in this image, and there's not anything throughout the course of the movie. A 1 means there's not a jet foot point nearby, but it's near jet activity. Both 0 and 1 means that there's no jet activity, but we wanted to give a distinction in case we could see any difference between if you're closer to these jets or not. So 2 is that there's likely a jet foot point in the box, but we couldn't say for sure that there was any particular network jets during the 1 hour of observations we had. So maybe it would produce some if we were looking further, etc. A 3 meant that there were 1 or 2 good observations of these network jets during the observation, and then a 4 meant that there were 3 or more network jets. So this is a fairly subjective process, and so one way to mitigate that was that both Sean and I separately went through this entire process. So the red pluses are my values, and Sean's are the blue crosses. And one of the big differences that you can see is that mine are typically a little bit higher, and that's because we were starting out with separate definitions of what a network jet was. So I was looking for this transient collimated brightening, something that was a column of bright material that didn't last very long. Sean was looking for a blob along that column that moved outwards so that you could actually track how fast the outflows were, because that's what he did with the science paper when they first discovered the network jets. So there's some differences in our definitions, so I want you to focus on the average values, which are these black circles here. And there's certainly times when we both agree that there's a lot of strong activity. And the main thing I want to point out here is this dashed line here is basically showing a threshold in jet activity. So this is going to be a square as a rectangle sort of thing. If a grid box had more than 25 Gauss, just a certain amount of flux density, then it did have some amount of jet activity. You can't say the other way around, because there's certainly grid boxes that had less absolute flux density that also had activity. But if you were above this threshold, then you definitely had some amount of activity, which is the 2s, 3s, and 4s. And remember, this category, the higher the number, the more jets there were. And when you focus, especially on these 3 examples where both of us agreed that there was definitely 3 or more strong jets, and you then, instead of looking at this, how much flux was there, we look at how imbalanced it was. Is it all one single polarity, or is there a mix of positive and negative? All 3 of those points are lying basically right on top of each other down here at -1, which means all of that strong amount of flux is all the same polarity, it's all the same direction, which means that it's all open and they aren't like looping together, having opposite polarities next to each other. And so you can also see that there's this strong trend that as you get to higher and higher jet category, you're seeing them at stronger and stronger flux imbalance. Now it's -1 here instead of +1 because the coronal hole that we're next to, all of that is basically negative polarity. Because coronal holes are all open magnetic fields, so they all have the same polarity. And so we're right next to that, so we expect to match that polarity. So what we found was that the modeling that we found can create these outflows that we think we should be able to see in observations. And when we turn to the observations, we see that there's a lot more jets when there's a lot of unbalanced flux, which means that there's a lot of magnetic field to have Alfvén waves, and not a lot of the opposite polarity flux, which you would need for magnetic reconnection, which is the other explanation for why these jets occur. So we're basically providing evidence that it is the Alfvén waves that we've modeled before, and that there's not a lot of this opposite polarity flux to allow magnetic reconnection. This project is basically a proof of concept for further studies, so there's a lot more that we can do for it. This is basically the ongoing work that is in my thesis. And so now I just want to summarize with a couple of slides. So we've seen this now 5 times. And so hopefully you guys are now coming away with a better understanding of what's actually in this image. The plasma is tracing out the magnetic field lines that are changing over time. And we have this chromosphere that has a lot to do with what could be heating the corona. So looking back, it's that wordy slide again, but it's the same words that I've had in each of those smaller examples. So this is sort of just tying everything together. The fact that the work I did started with a one-dimensional parameter study of magnetic field that led to my creation of a code that could be used in space weather forecasting. We then moved on to 3 dimensions and time dependence to find out that the kind of work that we were doing can produce bursty nanoflare-like heating, which previously was mostly attributed to magnetic reconnection. And then when we actually look at a real-world example of these things, what we're seeing in the magnetic field information is really supporting the type of modeling that we're doing. I was only able to provide 3 or 4 of the 30 or so images in my thesis. So if you really want to learn more, these are the papers to do it. There's also a paper where I talked about the use of tempest in the classroom for student research, as well as an essay looking at the Zeeman effect, the kind of way that we measure magnetic fields in the sun, but now attributing it to the interstellar medium. Looking forward, there are 2 really big programs that are going to change how we understand solar physics as a whole. DKIST is being built now and will be finished by 2018. And that will provide us very, very good high-resolution understanding of the sun and of the magnetic fields that can answer a lot of these questions from the ground where it can last a very long time. And Solar Probe Plus is going to be revolutionary in the sense that when it launches in 2018, it will take a little while to get there, but Solar Probe Plus will get closer to the sun than we have ever gone by an order of magnitude. It will get within 9 solar radii of the sun. So if you imagine the sun as a basketball, it will get 9 basketballs away and be able to measure what's happening at that point. So it will be able to give us a sense of what the plasma is actually doing in the corona and not just being able to look at it from afar. So these 2 together will really change everything that we know about astronomy, and hopefully all of the work that I've done will basically lead up to that. And so now, since you should always end on a conclusion slide, and I am not one to say no to a challenge, I will leave you with this. Thank you.
Take some questions.
Are there any aspects for using computer vision or some sort of automated system to find these network jets over more of the sun?
Yeah, so I've actually been talking with a postdoc at NASA who does some automated tracking of coronal holes and the possibilities of doing this. So when I mentioned before those grains made it very difficult for us to do it since we have no background in machine learning algorithms, but we've been talking to people who could be able to do that, and so that's something we will definitely pursue as a next step.
The nanoflare heating plot you showed, it looks like a nice Gaussian, although it was a log energy curve.
Right.
So it looked like then almost all the energy is coming out in those couple of big nanoflares at the top.
Yep.
Can you run more simulations? I mean, obviously, that it really is important what the slope and just how many of those nanoflares there are.
That's true. That's true. So each one of those types of models, the 3-dimensional time-dependent ones, take a couple of weeks to run. And so because we weren't looking for that in particular, it was actually something that was surprising in the data. We didn't think to have a lot of those, but that is something that we could pursue because it would be useful to really get better statistics on what that's doing.
Lauren, it was a great talk.
Oh, thank you.
I have kind of a more general question, not precisely on your thesis.
Sure.
You mentioned early on, I mean, the space weather is a big deal for life on Earth.
Yep.
And you said that these events can, and they do, disrupt our power grid.
Mm-hmm.
How exactly does it do it?
Right, right. So in 1857, there was the Carrington event, which was a huge coronal mass ejection that was aimed straight at the Earth. It was just the right configuration that it really affected things there. And what I mean by that is, first of all, it wiped out all of the telegraph lines because they basically were overloaded with power. Because if you have something that hits our Earth's magnetic field, you are now moving the magnetic field, and so you create electric field in any long wires, which would be telegraph lines or our power grid. So you're basically overloading it with a lot of electric field that you didn't expect to have there. And the telegraphs actually ran for like a week without being turned on after that event because there was so much residual power there. And so if that exact event happened now and we weren't prepared for it, they could overload basically our entire power grid and take out the big transistors or whatever they are. And we don't have all of those in storage, and so you'd actually have to make them, and we would be out of power for weeks, months, some estimates are even a year. So if we don't know that it's coming, and we don't know how strong it will be, you can't basically, it's kind of like unplugging your computer when there's a lightning storm. You can prepare for it if you know it's going to happen, but if it hits and you're unaware, bad things can happen.
But finally, it is the V cross B, is it? Is it magnetic field lines cutting the...
Yeah, so sometimes you might hear in space weather a southward or northward IMF, so the interplanetary magnetic field. So our magnetic field lines in front of the Earth go a particular direction. And so if the coronal mass ejection is coming with lines that are pointing the other direction, because they're basically a big blob of lines, when they hit here, they basically go through a lot of magnetic reconnection and strip away all of the magnetic field in front of the Earth. And then all of the particles and material can come down the lines to much lower latitudes than just at the poles. So there's lots of different things going on. Just the shaking can create the electric fields, but then if you've got a lot of reconnection up front, you can basically take away our defenses.
So the distinction between wave heating and reconnection heating is still controversial.
It is, absolutely.
And having demonstrated you can get high frequency heating with waves, the other question is then, can you also accelerate particles with waves? And then we have actually no way of distinguishing between reconnection and wave heating, and we're completely sunk.
Right. So I haven't thought too much about particle acceleration, so that's something that I'll have to get back to you about. But it is true that it's an ongoing field where all of the modeling is matching current observations. And so maybe the right answer is that we have to wait until we have DKIST and Solar Probe Plus that can make even better observations that we then have to be able to distinguish these things. But I do think that the wave heating that I've talked about before is more at play in the fast wind, in the open field, in the coronas, and that the slow wind, because it does have a lot of different characteristics, it is still true that magnetic reconnection is doing a very good job of modeling the slow wind.
So how confident are you that Mr. McKillop provided truly independent
Well,
double-blind categorization?
he was on that Tiana et al. Science paper. He has more papers to his name than I do.
I don't question his integrity. I question his independence.
I see. We did those two whole run-throughs in separate offices at separate times, and then mathematically averaged them together.
Very good.
Yeah. Closed room, no communication. Yeah.
She totally didn't tell me exactly what to do.
Okay. Any other questions? If not, let's thank Lauren again. Bringing the lights back.